All right, so we're looking at some related rates problems. So we've got a car is traveling west at 50 miles per hour, and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. So let's draw a little picture. We've got car A is traveling west. We've got car B is traveling north, and they're meeting at this intersection. Well, we want to find the rate that they're approaching each other. So the distance we want to find is this distance between these two, which notice it forms a right triangle. So let's maybe call this x, call this y, and we'll call that z. So we'll set the Pythagorean theorem, x squared plus y squared equals z squared. Remember, before you take the derivative, you only put in things that are constant the whole time. Our links x, y, and z are always changing, so we don't put in anything ahead of time. When we take our derivative, we take it with respect to time. So we'll have 2x times dx dt plus 2y times dy dt equals 2z times dz dt. Now, we wanted to find at the instant that car A was 0.3 miles away, car B was 0.4 miles away. Well, notice this is just a 3, 4, 5 right triangle where we have 0.3, 0.4, and 0.5. So that'll be at the instant when z is 0.5. Now, another thing to keep in mind is because our links are decreasing, we need to put our rates in as negatives. So we're going to have to put these in as negative 50 and negative 60. So we're going to have 2 times our x value of 0.3, and then times our rate for car A, which was 50, but because the length was decreasing, we've got to put it in as negative 50. Then we'll have plus 2 times our y value of 0.4 times the negative 60, negative because it was decreasing, equals 2 times our z value of 0.5, and then we're looking to find dz dt. So all we have to do now is some simplifying. This will give us negative 30. This will give us negative 48. And 2 times 0.5 is just 1, so we'll have just dz dt left over. So we're going to have negative 78 miles per hour for dz dt. Probably the most common error in these problems is if the length is decreasing or the value is decreasing, you got to make sure you put the rate in as a negative. So our next related rates example, we've got a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path. So let's say this is our searchlight here. 20 feet from some path, and we'll say that this, we'll call it x, I guess, is the distance that the man is walking. And this would be our, we'll label this SL for searchlight. That's our searchlight right there. And if x is the path the man's walking, that's our searchlight going there, staying on the man as he walks. We want to know the rate that the searchlight is rotating. Well, that's going to deal with an angle. The searchlight located at this SL here, if we want to know what it's rotating, we want to work with that angle theta there. We want to find at the instant that the man is 15 feet away. So if I just resketch our triangle over here, this is always 20. we're going to find at the instant that this is 15. So if we do Pythagorean theorem, we'll have 15 squared plus 20 squared equals c squared. That's 225 plus 400 equals c squared, which is 625 equals c squared. And when you take the square root, c is just 25. So this blue triangle here, that's just at our instant. At that instant, that's what we're going to have. So we need to set up an equation that deals with our angle. So we're going to go ahead and use tangent because we want to also have the x in there. So we're going to set up that tan theta is equal to your opposite x over your adjacent of 20. Now we could put 20 in ahead of time because 20 is never changing. The searchlight is staying 20 feet away from the path. However, the man's distance is changing, the x, so we can't put that in ahead of time, and the angle that the light is rotating at, that is also changing. So those can't go in before the derivative. Now to make it easier to take the derivative, I'm going to rewrite x over 20 as 1/20th times x. So it's kind of clear, it's just a constant times an x, something that's linear. Well, our derivative of tangent of theta is secant squared theta. But we've then got to do our variable dt. So we'll have times d theta dt. And in fact, that d theta dt is what we want to find in the problem, because we want to know how the angle is changing over time. So the d theta dt should be the one thing that we are not able to plug in for. And then the derivative of 1/20th x, well, if you have 7x, your derivative is 7. If you have 10x, your derivative is 10. So 1/20th x, your derivative is 120. But then we got to multiply by dx dt. So keep in mind, this was theta right here. We need to do our secant value squared. Well, secant is the flip of cosine. Our adjacent is 20. Our hypotenuse is 25. So we know that cos of theta is 20 over 25, which is just 4/5. So that means secant is just going to be the reciprocal of that. So secant will be 5/4. So we're going to have 5/4 squared times d theta dt, which we don't plug in for because that's what we're trying to solve. We've got 1/20th. And then they told us that the man was walking at a speed of 4 feet per second. So we'll do times 4 for the dx dt. And now we just have to work to get d theta dt by itself. We'll get 25/16 d theta dt. This will end up being 1/5 because it's 4/20ths. And if we multiply both sides by the reciprocal, that'll cancel out. We'll get that d theta dt is 16 over 125 radians per second. Seconds we got from the question. The reason we know it's radians and not degrees is, remember, all of our derivative rules that we use with our trig functions are in terms of radians. Next example, we've got a rectangle. Its length is increasing at a rate of 8 centimeters per second, the width at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area increasing? So we've got this rectangle, we've got the width, and we've got the length. We want to know how fast the area is increasing, so we need an area formula. That's just length times width. So we'll go ahead and take our derivative. The reason we can't plug anything in ahead of time, area, length, width, none of those things are staying constant. So we're going to have dA dt. Really, technically, it's 1 times dA dt, but we don't need to put the 1. And then we've got a product rule going on the right. So we'll do regular length times derivative of w, which will be dw dt, plus dl dt, because that's the derivative of L, times regular w. Well, dA dt is what we're looking to find, so we won't sub in for that. Our length we wanted to find at the instant that it was 20 centimeters. Now our rates, remember, you always want to ask yourself in your questions, are our rates increasing as positive values, so are the lengths getting bigger, or should they be negative values because they're getting smaller? Well, here our length and width are increasing, so we're going to put it in our rates as positive values. So our width was increasing at a rate of 3 centimeters per second. dl dt, our length was increasing at 8 centimeters per second, and it was at the instant that our width was 10. So if we just simplify this, we'll get dA dt equals 60 plus 80. And in other words, dA dt, 140. Our units, we have centimeters squared per second. The reason it's centimeters squared, because it's an area, and then the seconds is your time part. Next example, we've got a ship that is located 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour, and ship B is sailing north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 o'clock p.m.? So let's say we've got ship A, which is starting out here, ship B, which is starting out here. So therefore, we know that this distance is 150 kilometers. And we know A is going in this direction. We know B is going in this direction. So let's say hypothetically this is the spot where ship A is going to be at 4 o'clock. And this hypothetically is where ship B is going to be at 4 o'clock. The thing we're looking for is that distance between them. So let's call that Z. We can call this Y. That'll be the distance that ship B traveled. And then what we're going to do is we're going to call this part X, because that's the actual distance that ship A traveled. In our triangle now, we can label that side in terms of X. If the whole thing was 150 kilometers, it has traveled X kilometers, so this side would be 150 minus X kilometers. Now in our setup of our triangle, nothing is remaining constant, so we can't put anything in ahead of time. But we can now set up Pythagorean theorem. We're going to have 150 minus X squared plus Y squared equals Z squared. With the first part, we're going to have to do a chain rule. So we'll have 2. Keep the inside the same. Our exponent now is really 1. And then we've got to do times the derivative of the inside, which would be negative 1. And then we'll have a dx dt. So the 150 goes away, but then the negative x, its derivative is negative 1 dx dt. Now the y will have, that one's a little easier, plus 2y dy dt. And then we'll have equals 2z dz dt. So things we know. Our distance x is getting larger. Okay, not our length in our triangle, but our distance x is getting larger. Therefore, that's going to go in as a positive value. Our length y is also getting larger, so that's going to go in as a positive value for our rate for dy dt. And then we're looking to find dz dt, so keep in mind we won't be plugging anything in there. Well, we started at noon, we went at 4 o'clock. So 4 hours have actually passed. If 4 hours have passed, and ship A is sailing at 35 kilometers per hour, that means that ship A has gone 140 kilometers. And ship B, if ship B was going 25 kilometers, that means ship B has gone 100 kilometers. So we're going to have 150 minus 140, because that was our ship A length, times a negative 1, times our dx dt, which was 35 for ship A, plus 2 times our y value of 100 times 25 for dy dt equals 2. And now this is where it's a little bit tricky. So our triangle that we're working with, the 150 minus 140 really gives us 10 here. This part we know is 100, and we're trying to find this z. So if we do 10 squared plus 100 squared equals z squared, that's 100 plus 10,000 equals z squared. So that means that z will end up equaling the square root of 10,100. So we will put in for z the square root of 10,100, and then we'll have our dz dt. Okay, this one's not going to come out nice, so if we punch in the whole left side, divide over the 2 square root of 10,100, we will end up getting approximately 21.39 kilometers per hour for our dz dt. So at 4 o'clock, that is the rate at which ships A and B are moving apart from one another. We know they are moving apart because that length is increasing. Okay, one last related rates question. We've got a kite 100 feet above the ground, moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? So notice we want to know how an angle's decreasing, so we're going to have a theta involved here somewhere. So let's say this is our kite here. We know it is 100 feet off the ground. Now it's only traveling at a horizontal distance. So there's that horizontal distance. Let's call that x. And then this is our string of the kite as it travels at that horizontal distance. So like here's where our kite's ending up here. Here's our string. Now we want to find what is the angle between the string and the horizontal. Well, we've got our string, our horizontal is the dotted line, so we're working with that angle there. So we're going to deal with tan theta again equals 100 over x. Our derivative of tan theta is secant squared theta. Then we've got to do the d theta dt again. Off to the side, let's write this as 100x to the negative 1. So for our derivative, we'll have minus 100x to the negative 2. which is really minus 100 over x squared. And then we've got to do our dx dt. So that just makes it a little easier for doing the derivative rather than doing quotient rule. So we'll have it minus 100 over x squared dx dt. So now we need to figure out what we have at the instant we're working with. We know that this is 100 always. That's why we could plug it in ahead of time. But x was changing and our angle's changing. That's why we couldn't put that in before the derivative. So we want to know when this is at 200, so that's this distance here. Well, this is just a form of our 30, 60, 90 triangle. Our basic 30, 60, 90, we've got 1, 2, and square root of 3. Well, everything has just been multiplied by 100. We got 1 times 100, 2 times 100, so this is 100 times square root of 3 for this third side. Now, if you didn't see that, you could always just do Pythagorean theorem and get it as a radical and work with it from there. You'll end up with the same answer. So when we do secant of our angle here, secant's the flip of cosine, so we want hypotenuse over adjacent. So we're going to have 200 over 100 square root of 3 squared. We're looking for d theta dt, so we don't know that. Then we've got minus 100. Our x, we said, was 100 square root of 3, and that's being squared. And our dx dt, we said it was moving at 8 feet per second. So 200 squared, you'll have 4 with 4 zeros. When you square a square root of 3, you get 3. When you square 100, you get 10,000. Multiply them together, you get 30,000. Well, that's really just 4/3. When we square the 100 square root of 3, we already know from before that's 30,000. We have minus 100 on top. You can cancel out 2 of the zeros. So that's really negative 1 over 300 times 8. So that's negative 8 over 300. And if we just multiply by our reciprocal, 3/4, well, you can take a 3 out of each. You can take a 4 out of each of these. So we'll end up with negative 2 over 100, which is negative 0.02 radians per second. And that's our d theta dt. And if we think about this, as that x distance increases, as x keeps going further to the right, that theta angle will be getting less and less. So that's it for today's video. We'll see you next class period.